Hello everyone, welcome back to this next lecture. So this is where we had left off in the previous lecture where I had described the driverlib project and I had compiled it. So in this lecture we are now going to execute our projects, that is both the Bitfield project as well as the driverlib project. So at this point of time I will bring the microcontroller into the video. So you will now see the microcontroller in the video, the usual connection, and here since we have a half bridge module for each CPU, we have only two connections in each of these CPUs. That is, from CPU 1 we have EPWM1A and 1B, and from CPU 2 we have EPWM4A and 4B, and these are connected to the solderless breadboard. So with this I'm going to zoom in to the oscilloscope. And now I will enter the debug mode. So first I will enter the debug mode with CPU 1. So as of now the connections have been made. For channel 1 is connected to EPWM1A and channel 2 is connected to EPWM1B, which means channel 1 is measuring the gating pulses to S1 and channel 2 is measuring the gating pulses to S2. So the yellow waveform will become the S1 gate pulses and the blue waveform will become the S2 gate pulses. So with this done, let me now go and click on the run button. So you will now see that we are now getting varying gate pulses. Alright, so you can see here clearly that these gate pulses are changing from an absolute minimum to an absolute maximum. So this is the reason for this is simple. We are now having a cosinusoidal modulation index that we are now comparing with respect to our carrier waveform. And since we have a cosinusoid, therefore the pulse width will also vary from a negative maximum to a positive maximum. So the only question you might ask is, even though it is actually changing, do we still know that we are getting the right value? That is, for instance, if I give the lowest possible modulation index, in that case, is that a guarantee that in that case for such a modulation index, I get the minimum possible gate pulse for my S1 device and I get the maximum possible gate pulse for the S2 device? So for this question, as I already said, the way to answer this question is that we must now make a certain modification to our code and we must use the watch window in the debug window to be able to achieve this. So I'm going to stop this for now. And I will also stop the microcontroller video. So I will now go back to the code and I will show you what I mean. So let me just collapse these so that I have more space and let me come all the way up here. So we are now adjusting this phase angle with respect to time for a 50 Hertz grid frequency. So now this is the expression which updates the phase angle every time the interrupt service routine is executed. So this is what we must do in reality. But for the purpose of control, or rather for verification, one other possibility is that we actually comment it out. So instead of actually providing this as a time varying phase angle, this is an input that we will provide in the debug window. The reason why we can do that is if we do provide such an input in the debug window, then we can compare that for different types of phase angles, this gating pulses that we are observing on the oscilloscope for S1 and S2 are as we expect. So I'm going to just save this for now and let me come over here and compile the code. So the usual clean and build. So I'm going to bring the microcontroller back into the video. So you will see the microcontroller in the video and it is in the same state as before because simply the code is running. Now I'm going to enter the debug mode. So the gate pulses have stopped because now it is erasing the code that was existing before and loading the new code in. So we are now in the halted state. So let me run the simulation, or let me run the code, and you will now see that we have now a steady waveform. Now the reason for this is our phase angle is at 0. That is the initial value. So for this reason, I'm now going to start with the watch window. So let me copy this and let me come up here and add it to the watch expression. So now this is my phase angle. Let me just expand it a little, and here we have it. So you will see here for this 0 phase angle, we are now getting S1 pulses to be the maximum width and S2 pulses to be the minimum width. Now here, think for a minute and see, we have a cosinusoidal modulation index. That means whatever is the phase angle, it is the cosine of that is going to become the modulation index. And if our phase angle is 0, then the cosine is the maximum value, which means at this maximum value, the S1 device is going to be on for the maximum amount of time, and S2 device is going to be on for the minimum amount of time, which is correct. So now let us go and make a change. For example, let's say I want to have something like a 60-degree phase angle. Or let's say, for example, I want a 90-degree phase angle, because a 90-degree phase angle will imply that this is now a sinusoid. So I'm going to say 90 multiplied by pi divided by 180, because this is the comparison, this is the conversion of a degree, angle in degree, to radians. So let me just copy this value and let me go and put it in this value here. So now you see it is a very different waveform, because now our phase angle is 90 degrees and the cosine of 90 degrees is equal to 0, because cosine of 90 degrees is the same as the sinusoid of an angle, right? So, or sorry, cosine of 90 degrees can be seen as the phase shifted sinusoid, right? Now it is not the same as a sinusoid, it is a phase shifted sinusoid, but in this case we know that cosine of 90 degrees is 0. And if cosine of 90 degrees is 0, then our modulation signal is also 0. And if you're comparing a 0 with a triangular waveform, then you will get the 50% duty ratio. That means the gate pulses to S1 will be 50% duty ratio, and so will the gate pulses to S2. And that is exactly what we are observing. So now let me go and make a change. Let's say, for example, we have something like 45 degrees. So let me change this to 45 degrees. So if you have 45 degrees, now let me copy this and see what happens. And you will see now something very different happens. But now this 45 degrees is the cosine of 45 degrees. And the cosine of 45 degrees is 1 divided by root 2. So which means now this S1 device is going to have a gate pulse with a much wider width, but not near maximum yet, right? So this is something that I would ask you to verify on your own. Take your own time to verify this and figure out if this is what we should get. So in this manner, you can actually place several different values. So for example, let's say we put cosine of minus 90 degrees, or let's say cosine of 180 degrees. So for instance, I'm going to just change this to 180, and this of course will be pi, but I want that value of pi. So I'm going to copy this value of pi, take it over here, and change this as well. So if you say now the cosine of pi, you get a very different result. And here you can see now cosine of pi is minus 1, which means now the modulation signal is minus 1. And this would imply that our S1 device, or rather the gate pulses to S1, will have the least amount of width. And the gate pulses to S2 will have the maximum amount of width. Right? So this way you can precisely calculate and verify whether the gate pulses that you are producing are accurate. In the previous case, we saw that they were changing, and that gave us some confidence that we are producing a varying signal. But just that variation in the signal is not enough. It is important that you precisely verify that for a particular phase angle, you are getting exactly the kind of gate pulse width that you are expecting. And that is what is being provided here. So For now, I'm going to delete this phase angle and let us now execute CPU2 code. So I'm as usual going to connect the target, and once the target is connected, I'm going to load the code. So again, go into the correct driver lib folder, go into CPU RAM and load the .out file. So the file is now loaded. I'm going to click on it and click on run. So at this point of time, let me change over the oscilloscope probes to the EPWM4 pins. So this is now the yellow waveform is connected to EPWM4A and the blue waveform is connected to EPWM4B. And this is exactly the same result that we were getting previously with the bit field example when we had let the phase angle change on its own. That is, when we had let the phase angle change as an integral of the angular frequency. So now this I will leave to you as an exercise to use the same approach, that is, use the debug watch window to verify that if you input a particular phase angle, does it result in the exact gate pulse that you were expecting. So go ahead, put different values of phase angles starting from 0 degrees all the way up to 180 degrees and verify for yourself that you are getting gate pulses ranging from the maximum possible to the minimum possible for both power devices. So this I will leave to you as an exercise. So with this, now we have a working half bridge module that is operating as a DC to AC converter. And in this case, this is the first time we are providing PWM signals to a DC to AC converter using a triangular waveform, which is the EPWM module configured in the up-down count mode. So with this, I'm going to end the microcontroller video. And we have also come to the end of this particular lecture, and with that also the end of this section. That is a section on the half bridge module. So we had considered various topologies of the half bridge module. That is, we had seen the half bridge module being used as a bidirectional buck converter, as a bidirectional buck boost converter, and now as a DC to AC converter. So this shows the flexibility of this particular half bridge module. So with this, I'm going to next lecture going to conclude on this section, and in the next section we will examine the full bridge converter, which consists of two half bridge modules connected together. So if any of this was not clear to you, or you faced any other issues, please post in the Q&A forum and I'll be happy to help you. Otherwise, I will see you in the next lecture. Thank you so much for listening and see you soon. Goodbye for now.